Hey friends, we are back. It's deep.net. Stephen, I tried to put in some sound effects so that we could announce the show with more gravitas. I was trying to come up with some kind of a voice manipulator, deep.net. And
like the Olympic theme or something.
yeah, Olympics theme would be nice. Absolutely. I've been watching the Olympics. And I tried to do like the voice synthesizer, and it just came out as like, welcome to deep.net. So I have nothing for you today to announce your return. And we also, you did some coordination for me. We've got a couple of other friends coming up in future versions of deep.net to talk about other stuff. So we will see them in the coming weeks and months. So I'm excited about that.
I'm excited too.
All right, so today, as we get into the obscurities, into the depths of .NET, we're going to talk about the .NET ArrayPool class, which is interesting, in an unusual namespace in system.buffers.
Yeah, great. I think we talked about spans a few recordings ago, and I highlighted that span is one of the things that sort of really significantly changed how we write code and how we think about the code that we write in the core libraries. And I mentioned there were a few things on that list that sort of transformed or revolutionized what we do and how we do it. And ArrayPool is also on that list. And it has significantly impacted how we think about the code we write and the resulting performance. A lot of the improvements that you see in the last several releases of .NET have come from using ArrayPool or a combination of spans and ArrayPool. In fact, a lot of the places you see ArrayPool show up, it's right there with span, and there's some very common patterns that show up about how the two are used together. So I thought it'd be interesting to explore sort of just pooling in general, and then why ArrayPool in particular is so impactful, and maybe kind of sketch out an implementation of what it actually looks like that would be pretty close to the real one.
So both ArrayPool and span are all about performance and memory efficiency. Span is one of those things where I'm writing, business code, text boxes over data, and I'm not often at the level that I'm writing code writing to span directly. I'm not pulling span out. It's there making my life better. Is ArrayPool something that I'm going to want in my toolbox as a application developer, as a business developer?
It depends. I mean, in general, pooling is a performance optimization. There's no other reason to employ any kind of pooling other than improving performance. In fact, pooling has certain risks that come along with it. And usually there's some additional complexity along with it. And so you're paying some amount of complexity to improve the performance of your application. There are absolutely places where that could be relevant at an application layer. And so I would imagine that application developers will, in certain circumstances, based on profiling and performance analysis, will use it. But it's much more relevant at the lower layers of the libraries that are being consumed by those applications, where there's a lot of manipulation of bits and bytes happening. And you need, for those operations, scratch space or temporary buffers or just places to put data. And that's where ArrayPool kind of really comes into play and helps eliminate allocations that can have a meaningful impact on the end-to-end performance of applications.
All right, let's dig in. Let's share your screen. And here we are. So we start, as we always do, at console.writeline.
Yeah, hello, Scott. It is worth setting the scene a little bit because, we talk about ArrayPool, but ArrayPool is just one very specific kind of pooling for one very specific type. Pooling in general is, as I mentioned, a performance optimization that shows up all over the place. And there are often debates about whether to actually employ pooling or not. There are certain cases where it is a no-brainer. You just do it because the costs are otherwise so enormous that there's really no other choice. And a good example of that would be something like HTTP client, which pools HTTP connections. So if someone makes an HTTP request to bing.com, we need to open a socket, do a DNS resolution, connect the socket to the remote host, Maybe layer on top some security like TLS. So you're using something like SSL stream. Maybe there's some kind of handshake that's happening, whatever it might be. And you could be talking to a server that is not just sitting next to you as localhost. It might be halfway around the world. And you might be dealing with microseconds or milliseconds or even seconds of latency as part of establishing that connection. That is a huge cost to have to do every single time you send an HTTP request. That way, and if you look at something like in your browser, right, you're not just hitting, Bing.com. When that page comes back, there are 17 images that show up and scripts that need to be downloaded, all from Bing.com. And so you're making all of these requests, and if every one of those incurred those latency, that would be you'd feel that viscerally, right? And so you really want HTTP client to make the connection once and then hold on to it and use that same connection for subsequent requests. Now, there might be, if it just had one connection, you have a pool of basically one. And every request that comes in, you just map it to that one connection. And if the one connection is being used, the requests queue up and they just wait for the connection to become available and they can use it. But that's not what HTTP client generally does. It has by default, an unlimited size pool. And if there's a connection available, it will use it. And if not, it'll create a new connection and then all the connections. Then, of course, you have all the maintenance associated with the pool. You don't necessarily want those connections to sit around forever. So every once in a while, you want to go check and see if they've been idle too long and then call them out and so on. So in a situation like that, pooling is critical. But then you've got to go down a little bit and you look at the things that people often also use pooling for. And it's more like pooling objects in memory, which is sometimes the right answer, and sometimes it's an optimization that can actually be a t-optimization. If you have a tiny object, it could actually be faster for you to just allocate that object and throw it away and rely on the garbage collector to just do its thing. It's really good at cleaning up quickly after small objects. And so if you look around the core libraries, like there are places where we will be allocating a 1-byte array or something, and it doesn't make sense for us to pool it because the costs associated with pooling it would be larger than the costs of just allocating and throwing it away and letting the GC deal with it. But then you have this stuff in the middle that is, either constructing these objects takes some amount of time. Maybe it's a resource-intensive thing to construct, or maybe you're holding on to expensive operating system resources, or maybe the allocation is just big. As is often the case with arrays. And the larger the object, the more expensive it is from a GC perspective. Because the more memory that you've allocated, generally the more frequently the GC needs to run. Those objects need to be zeroed out when the GC hands them back to you. There's just additional cost. And so you hit some threshold, we hit some length of array where beyond that, you really don't want to be creating these things at high frequency. And because arrays are these generally larger dynamically, you end up with very large size things, often of varying sizes. You really do want often a cache for those sorts of arrays. And that's why we end up with, there's no other type in .NET that has a public type dedicated to pooling it other than ArrayPool, because these things are ubiquitous. And if you look throughout the core libraries, you'll see we use it all over the place for pooling, in particular, byte arrays and char arrays. We do other things too, int arrays and object arrays, but those things are sort of the bread and butter because you end up using these things very frequently when you're doing any kind of data manipulation. You're doing encoding, decoding, or transcoding, or you're doing, you need a temporary buffer to read some data off the network, do something, and then you want to give you're done with that buffer. You don't want to just allocate a 4K array and throw it away. So that's where ArrayPool really comes into play. And if you were to look throughout the core libraries, it's used in hundreds, if not thousands of places now.
This might be an ignorant question, but why is there not a generic pool of T or just pool, and then it's a pattern and I just throw anything I want in a pool? Why is array so special? You said because they tend to be large, they tend to be unwieldy.
So there actually is. There is an object pool of T that exists in the Microsoft Extensions namespace.
In extensions. Okay.
Yeah. The challenge with, so there's a couple answers to your question. The challenge with generic pooling like that is there's often policy that you want to involve about, exactly what do I pool? Exactly when do I get rid of things from the pool? Prioritization for how I pull things out. There's policy that goes into it. And the more policy you have, the more costly it is to rent and return things to the pool, because there's this ceremony associated with it. And the more of that there is, the less likely pooling is to be relevant. There's also an aspect of often the things that people like, oh, I need a pool for this. Sometimes they're not quite right. And having a pool front and center that we recommend, just use this for everything, or it makes it easy to use it for everything, it can kind of lead people into a bit of failure. But the other interesting thing is that makes arrays special is there are lots of different, there's a something very special about arrays, and that is they have different sizes. You can't just reuse one object for every possible thing that might come along that needs a T. If I had a person type, okay, I just have a pool of person objects, and I could use that when I need one for Scott, and I could use that when I need one for Steven. But with arrays, you might be an array of like 34, and I might be array of like 15, and we don't necessarily want to use the same array, nor can we group them together. Also, we do have generally. Actually, this is a really good segue to maybe take a look at some code, because pools can be very sophisticated or they can be really simplistic. And if we want to build a really simple pool, a class my pool of T that has a...
So would this be like default object pool?
Yeah, sure. Okay. And I want to be able to rent a T, and I want to be able to return a T. And then let me just, to make this easy on myself, I'm just going to put a constraint here so that I need to be able to allocate one of these things if someone asks for one. I have one. You can implement this in basically one line of code. So all you really need is a collection. So I could say I want a concurrent queue of T, and returning one of these items is just putting it into the collection. And static. And renting one of these is then, just like Copilot read for me, is then just dequeuing one of these, right? So a pool needn't be a fancy thing. I've implemented here an unbounded queue, an unbounded pool, where if one's available, it will return it, and if one's not available, it will manufacture one. A pool could be even simpler than this. I could have a pool of, if I just, again, make this simple on myself, and I'll say that this is always a class, I can have a pool of a single element, right? And then renting is basically saying item, if item is null, then return new T, otherwise null out the one that I got, and the one that null out the field to return the item. And then returning this could just be item equals item, or maybe do a null check and only assign it if there wasn't already one there. Right? So now I have a super simple pool of a single item rather than an unbounded pool. This is kind of what I was getting to around policy, like which pool do I want for the particular need that I have? Or maybe I want to bound it, store more than one, but maybe store 50 or 1,000 or whatever it is. So pools can be super simple.
What could be the correct behavior? I think that you kind of lost me at the example of a pool of one.
Okay.
Because at this point, it felt like isn't a pool of one just like a static that we're all going to just go and poke at? It
is. And I'm just able to, I could create a pool that's... It's not a static one. I've got
static is. I don't mean static, but it's like we all have our. I have a hand on the bottom of the hilt of the sword, and you do too. So hang on a second. Whose is this? So what is the correct behavior for a pool of 5 and 6 people want it?
one of them, whoever comes along sixth, has to allocate their own. But the interesting thing is
then it's just unbounded. Then so you get optimizations until demand.
Yeah, and it's kind of like a juggler, right? A juggler only has two hands, but they might have 10 balls in the air. Mm-hmm. So you only need to have space to hold two of those balls that they're throwing up, but they could have 10 in circulation.
I see.
But if all those balls then come landing at the same time, and I only have hands for two, 8 of them are going to get dropped.
Okay.
And then the next time 2 people come along, I have 2 balls for them. But if anyone else wants that, well, now I'm going to have to start allocating more. And this happens with the real array pool as well. We don't want to store an unbounded number of arrays because that would be effectively equivalent to a memory leak.
Right.
So we do put in place limits. And if you throw it's a higher number than 2, but let's say the limit was 2. If you do throw, have 10 arrays circulating and only 2 of them are landing at a time, but then there's a lull and they all get returned to the pool at the same time, a bunch of them are going to get dropped. And then over time, we also, if the things are sitting there idle, there's also some trimming work, some background cleanup that happens that if the GC says, hey, I have some memory pressure, then the array pool goes and starts purposefully dropping things that they had cached to kind of trim it back. So pooling can be super simple or it can be super complicated. But the thing that makes array pool, adds a little bit of complication to array pool, is the complication that you can't just use the same array for all requests unless you wanted to pool arrays of max length. And then regardless of whether someone asks for an array of like 16 or an array of like 64, you give them an array of like max length. Other than that, you need to be able to accommodate different sizes. So you kind of need your array pool to be multiple pools. Just like in the HTTP example, you can't reuse a connection from Bing to talk to Google, right? So when you talk about the connection pool, it's kind of a misnomer. There's actually multiple pools, right? There'd be pools for Bing versus Google. And then within that, there's also, it's not quite right because those connections can have different settings. One of them could have been HTTP and one of them could have been HTTPS, or they could have been using different certificates or different, a whole matter of different settings. So these pools can get very complicated partitioning up to ensure that when you actually go to the specific collection storing the things, that any one of them is usable for your purpose. So let's look at array pool then. So let's just build our own to kind of get a pretty. We'll build one that's not as complicated as the real one, but close enough to give a very good mental model for how it works. Now the real array pool is a class that has instances. So this returns ArrayPool tf.shared returns an instance of ArrayPool. It's debatable whether we made the right decision there. The idea was that the ArrayPool class is actually abstract. I can derive from it. So if I look at what's on ArrayPool, we can see that it's an abstract class and it has an abstract rent method and it has an abstract return. And so the idea was that you could create your own array pools and you could have a function that was parameterized with an array pool and you could pass in different ones. In practice, the 99% case, or 99 point, I don't know how many nines, 99999% case, is folks just use .shared, .rent, or .return. So for our purposes, I'm going to pretend that array pool is actually static, and we'll just say array pool, my static array pool of T. And so I need the same thing we just saw. We're going to be handing back a T array, and we're going to be accepting a T array. But again, not every array is created equal. We need to know how long the array should be. So call this length. So we could do some very simple checks just to kind of weed out corner cases. I could say throw if it's negative. And I could say if length is 0, just return array.empty. And now I'm only dealing with the cases that I care about, positive lengths. And then similarly on the return side, we could say, let's throw if it's null. And if it's empty, we'll just bail. And now I'm only dealing with the cases where I actually have an array that I really need to return to my pool. So now the question is, well, where am I storing this stuff? So I have a variety of options now here for, I'm going to be dealing with different lengths of arrays. I can't just have, I could just have a single, say a list of T array. This needs to be static. And in here, I could lock on that, and then I could loop through it, checking to see if I love when Copilot just does stuff for me, especially when I'm going to delete the code after. It's looking to see whether it was the exact right length, and if it was, I pull it out and I remove it. I could do that. That would be incredibly inefficient because however many lengths I'm storing, every rental ends up being an order n operation with the number of arrays that are in the pool to find the one that I want to return and return it. I don't want to do that, but it is an option that I could have. Another option would be I could do something like have maybe a concurrent dictionary that maps a length to an actual queue of arrays. So, now when I go to rent, I would basically say if S arrays try get value, and I look for the length. If there was a queue, then try and dequeue an array from it, and if I could, return that array. Otherwise I could just create a new one, etc. So I could do that. It's okay. So people are
very, very exciting array language as the dog.
Yeah, people are mowing our yard. He doesn't like that. It's his territory, and they're on it.
Oh yeah.
So we could do this, but even here, if 40,000 different array lengths were requested over the lifetime of my application, now I've got 40,000 buckets, and I'm not able to make really good reuse of these arrays. If someone requested an array of length 102, and then it goes back into the pool, and someone else requested an array of length 101, it'd be kind of nice to just give them the one that was 102 and just say like, hey, just use the first 101 elements.
Right.
It's a little longer than you need, but
I'm sitting here and I'm absorbing and I'm trying to process in my head, but I'm thinking about that and I'm kind of going, has value been provided yet, or is this just kind of an unbounded? I'll give you anything you want, and memory is just going to keep growing forever, and we're going to hang on to it forever. Right.
And if what are the chances that we actually have one of the arrays that was the exact size that you wanted? If you're only requesting arrays of like 4096, well then sure, fine. But if that's the case, this is over-engineered for that. We could do a much better job of handling that. So we don't really want to do that either. What we end up actually doing is we do create buckets for so that you don't always get an array of the length you requested. Instead, we have a minimum length. So we guarantee you that we will give you back an array that's at least as long as you asked for, but it may be larger. And that allows us to then map multiple requests to the same bucket. And how many buckets do we want? Well, this is an implementation detail. The strategy could change over time. But right now, we maintain buckets that are sizes of powers of 2. So we have a bucket for anything up to 16, then another one for anything up to 32, then for anything up to 64, 128, 256, and so on. And there are a couple of really nice properties to this. One is it means we only need about 30 buckets. Basically, 2 to the 31 effectively is array.max length. So it's not possible to need anything more than that. And then even within that, we're actually down to closer to 27 buckets because we map everything from 1 through 16 to 16. We kind of skip the 1, 2, 4, and 8s of the world because those are so small. It's not, you shouldn't be asking, generally, you shouldn't be focusing on using the array pool for things that small anyway. It's not till you get to around 16 that pooling actually starts to be worth its weight. And so if you do ask for something smaller, we make it work, but we just give you one of the 16s. So we have these, say, 30 buckets, and which is one nice property. We don't have a lot of them. The other nice property is it means that no matter what length you ask for, we're never wasting more than twice as much space as what you need. So if you ask for an array of length 65, worst case is we give you an array of length 128, and you've only wasted up to kind of twice as much as you needed. It's very similar to the strategy that you see in pretty much any language when you grow a collection. There's this typical doubling algorithm that happens where if you have you have a list of T and you've got an array of 4 behind it, and then you add one more element, list of T doubles to be 8, so that when you then add 6, 7, and 8, there's enough space for it. And then if you add one more, you add the 9th element, then it doubles to be 16. And now you can add 9, 10, 11, 12, 13, 14, 15, 16 without another array. And this has some nice properties from an algorithmic complexity perspective. So let's do that. So we're going to have a static array of something that allows us to store arrays. So we'll use an array. In this case, I'm going to keep it simple and use a concurrent queue because it's this nice thread safe thing that lets me put things in and takes things out. And I want to create basically, let's say 31 of these things. It's not actually necessary, but 30 of these things. Doesn't matter. So I can just say range from 0 to 30. I want to select a new concurrent queue. Right. So I've got my arrays here. And now I need to map incoming requests to the relevant slot in my array. And a little bit of thinking about it highlights that what we really want is, if we're looking for powers of 2, sort of the inverse of that is log. So we really want to take the log base 2 of the length, and that will tell us exactly which bucket to use. So I can say queue, and it's telling me I should use get bucket index. So for get bucket index, I'm going to just do get operations dot log 2, and I'm actually going to, just to make things work out the right way, I'm going to subtract 1 from it, which isn't really relevant. It just has to do with sort of the values at the bottom. And that's it. Now I have my queue. And so now I can do the exact same thing that we saw earlier. I can try and dequeue an array. If I got one, great. If not, I can return a new array. Now, I don't actually want to return an array of minimum length, because then the pool is going to be producing interim lengths. It's going to be producing lengths 9, 10, 11, 12, 13. But I really want all the arrays produced to be of the exact size of the bucket, because I'm promising that by mapping up to that bucket size, everything will work. So here, we really just need to round up. So I can say round up power of 2 minimum length. Ellipse. And that's my array pool implementation for renting. And then returning ends up being very similar. I
don't know why I find it so funny that there's a function called round up to power of 2 hanging off bit operation.
It took us a while to add it, but it's super useful. I mean, it comes up.
I'm just saying, it's like, okay. I mean, yeah, those are the kind of things where I would sit there probably for 10. This is just like, you code all day and I code twice a week. But like, I would be doing the math and I'd be like, oh, bit operations exists.
Yep.
So there's a little little.
We were doing the math too for years before we said, this is silly. We should just refactor this into a thing called round up to power of 2 and make it public. And then we can, the actual implementation of this, it'll navigate to it. You can see this is sort
exactly.
of, yeah,
exactly.
But then we have the optimized implementations that are intrinsics.
We if def our way to glory there.
Exactly. And this logic lives inside of the core library, system private core lib, which we most of the .NET libraries are built once and they're used everywhere. Core lib is special. And it's built for 32-bit versus 64-bit. It's built for Windows versus...
And you see WASM in there as well.
And WASM as well, yeah. And this is something we don't actually need to build the different library for each. This is something where at runtime, we are able to check, and these basically are all JIT intrinsics, where while they all show up in the IL, the C# in the IL, when the JIT actually generates assembly code, this will be true or this will be true, but it's able to do dead code elimination on the relevant paths and light everything up. It's one of the nice things about managed code is it can check what's available in the hardware, and then when it generates the code on that hardware at runtime, it can special case everything and specialize everything for the particular targets. So when we're returning here, there are some different error cases. Here we were checking for throw if negative. Here we also probably want to do a little bit of checking. We want to say if the length of the array is not a power of 2, then we probably want to throw an exception, because this array definitely did not come from the pool. So anyhow, we can then map based on the array length to the queue we want to use, and we can just return the array. And that's your basic array pool implementation. And the real one is a lot more code than this, but for specific purposes. So for example, I mentioned all that trimming stuff. So there's logic in the real pool where if it detects memory pressure from the garbage collector, it will go through and it will collect, start pulling things out of the arrays, the queues, and dropping them, because it doesn't want to be keeping all these arrays around. Some of these arrays could be really, really large. It could be a gigabyte or whatever. And you don't want to keep lots of those things sitting in memory. So as there's pressure, just like the garbage collector is going to go and clean up objects, the array pool does as well. There's also it doesn't actually today use a concurrent queue, although it could. The implementation today actually maintains a data structure where it has a list of arrays basically per core, and a thread. When we go to do the dequeue operation, we actually say, what core am I currently on? And grab the list that is associated with that core. Now, it might change between the time that we check and the time that we get it, but on average, it reduces contention, because on average, it won't change, and each core that's only running one thread at a time, only one thread on average will be able to use one of those lists at a time. We still have to protect it, we still have to lock, but we significantly minimize contention by distributing the load across all those different queues.
Okay, so I'm going to go out on a limb, because this is, my job in deep.net is to ask dumb questions, and then I always get analysis paralysis, and I think the audience is going to be like, man, that was a dumb question. Or that was, what do they say? There are no dumb questions, only inquisitive idiots. So
you are certainly idiots, sir.
In a world of asymmetric cores, there's efficiency cores and performance cores. Like, all cores are not equal anymore, and that's happening in ARM. It's happening in the Intel machines, including the machine I have right now. I always, I get why, and that the CLR and that the runtime knows that there are these there's physical cores, there's logical cores, and now there's efficiency cores. Do you have any insight into that? Does .NET think about those things, or at what level of abstraction does .NET just pretend that, all cores are equal?
So there are a variety of aspects to the question. With specifically with regards to P versus E cores, or efficiency versus performance cores, there's not a ton that the CLR does today, although it's definitely on our radar to factor that in. But there are other aspects that are definitely factored in. Things like NUMA. So it's not that the cores are different, but we know that their relation to memory isn't all equivalent. Right? Some cores are closer to certain memory than other cores. And even without NUMA, you have things like cache efficiency. So you know that every core has its own various layers of caches. And it's much better to use something if you're on core X that's in cache X rather than getting something that might be somewhere else. So all of those things definitely. Sorry.
For folks that may not know what NUMA is, right? So NUMA is this non-uniform memory access that the computer knows that like this CPU is near this memory and that memory over there, we're going to consider that remote memory, and it's all meant to reduce latency. Is that correct?
Yeah, and this definitely factors into things like the GC, right? And even thread pool scheduling. You want to put the work where the data is.
Put the work where the data is. Yes.
Otherwise, you spend all your time moving stuff around and thrashing your cache. You want
to and moving things around in at different layers of abstraction, because you would not want to move between NUMA nodes. You don't want CPU 0 to be looking at memory 1 over there. But then there's the higher level question of is the adding of an array pool to my application going to cause memory fragmentation, or do I just trust the GC to handle that? Like, it's a constant series of trade-offs of like, did the complexity I add give me the performance that I wanted, or did I just make things more complicated?
Well, it's a great example of where, I mentioned at the beginning, there's a lot of complexity with pools. And this is a great example of it. If you're running on a core over here and you use an object that was last used over here, right? Are you better off using that object, or are you better off just asking the GC to give you a new one that's going to be allocated on memory that's very closely associated with where you are?
Yeah, that's a good one.
So these pools aren't always wins. And there are other really interesting subtleties as well. Yeah. So one of the interesting things that we did end up adding is I
just had a stupid analogy pop in my head where it's like, is it cheaper to get it on Amazon Prime or just go to my storage unit? Because I know I have one. That's the kind of like stupid first world thing that we would make.
All of these trade-offs, and some of the trade-offs are so subtle that you wouldn't think about them. So ArrayPool doesn't actually have any async methods, but let's say that it did. Let's say I had my method. Doesn't matter what this is doing. If this thing completes asynchronously, because I do something that I await something that's not yet complete, right out on me. Then under the covers, by default, async methods are going to allocate a task object to back this value task. Value task is just a discriminated union between a T and a task of T. So it can be either basically a T or a task of T. Although actually now it can be a T, a task of T, or an implementation of an interface I-value task source T. But if you just write an async method like this, it's going to be either an int or a task of it. But, and the nice thing about value task is if I just return an integer, then there's no allocation here, because this value task of int will just be wrapping that integer value, and it will have a null task field. But if I put back this delay now, this value task is going, because it's completing asynchronously, and I need a unique object to represent the eventual completion of that async method, it's going to be allocating a task of T under the covers. For situations where this is on a hot path, and I know from profiling that task allocation is problematic, we've actually made it possible to, under the covers, use pooling. So you can say system.runtime compiler services async method builder, and this will be a pooling async method builder of int, basically. And now this is substituting a different implementation that, rather than creating a task of int when it completes asynchronously, it will grab from a pool an implementation of that I-value task source of int thing that I just mentioned. And so it'll be backing this value task by a reusable object. And we had a ton of debates about whether to expose this. And we have a ton of async value task methods that don't apply this attribute. There's just a few very specific ones that do. And we've only done it in places where we've truly measured to prove to ourselves that it's a net win. Because there are things that you wouldn't even expect that would impact this that can. For example, the way the generational GC works is it's generational. There are these multiple generations, generation 0, generation 1, generation 2. And the GC wants Gen 0 collections to be as efficient as it possibly can. It wants this to be super fast, right? Gen 2 collections are a lot slower. They take a lot longer. It doesn't want to have to do those very often. And it doesn't want to have to examine, when it does a Gen 0 collection, it wants to examine as little memory as it possibly can. So it really only wants to pay attention to parts of all of its graphs that it has to explore that are only Gen 0 and that couldn't possibly have changed since the last time you checked. So every time you write a reference to something, the GC tracks that. And it's got this table that it keeps in memory where it basically, for each kind of region of memory, it checks whether you might have written a Gen 2 object reference to something that was Gen 0, for example. So if you had a Gen 0 object, or sorry, if you had the other way around, if you had a Gen 2 object with a reference field on it, and you store a reference to a Gen 0 object into that Gen 2 object, the GC needs to know that, because now, whereas previously it didn't need to scan Gen 2 when it was collecting Gen 0, now Gen 2 has a reference to Gen 0. So it needs to scan those Gen 2 references to know whether the Gen 0 objects are still alive. Why is this relevant? Because pooling is all about making things stick around longer. And so all these objects that this ends up pooling end up in Gen 2. And that means that any state that you might have had in one of these objects, you pass it an object here, right? This is now a field on that object, which means that we're assigning what's potentially a Gen 0 object into a pooled Gen 2 object, creating that very situation that makes the GC's life and GC's more expensive.
Okay. And like value task exists to have less allocation overhead, to be lighter weight than task.
Yeah.
So now suddenly it's got a foot in Gen 2, it's heavier, and it's kind of
if you apply that attribute.
If you apply that attribute. Okay.
So now you're in this world where it's, and this is the reason we don't just put this on every single thing. And that is, or even make it the default. It's one of the reasons we don't make it the default, is it's not always a win. It requires you to kind of really measure your situation and understand all the intricacies, and which really means run your performance tests. And if this improves things for your scenario, great, apply it. And if it doesn't, don't. And our default is, well, even if you apply it, it's generally only a small win to pool. So we're just not going to. But if it works for you, do it. And so you see, I haven't checked recently, but I think we probably only apply this to maybe, I'm going to throw out a number, 20 methods in all of the core libraries, somewhere in that ballpark. For specifically places like really high throughput paths on web sockets or HTTP connections or pipelines or whatever.
So you said if it works for you, and the answer is measure, right?
Measure.
Like go and try it.
Measure. So, that's all getting off topic, but it has to do with, you were asking about thinking about how, threads relate to cores, and these are all things that can impact whether pooling is relevant or not to your situation. The nice thing for ArrayPool is generally we're dealing with arrays that are so large that it's almost always a win. That if we're dealing with arrays that are like 1024 or 4096, and we're just taking an array and doing a little bit of work with it and returning it, the overhead associated with allocating a new 4K or 16K array is significant compared to the potential costs of the things that we're talking about here. So that's why we sort of, if there was a place where we were always allocating an array and we have the opportunity to switch to always using ArrayPool, we pretty much do. The interesting case is in places where you might be able to do something more efficient if you took a path that wasn't allocating an array and used the ArrayPool in that case. Because you're now a more efficient operation that's able to use this scratch space will be more efficient if you are successful in renting an array. But if the array pool gives you back a new array in a situation where you weren't previously allocating, now you might actually be making things worse for yourself. So most of the places you see us using ArrayPool in the core libraries are places where we were already having to allocate. We basically had no other choice. Or we're on a code path where the chances that we need to allocate are so small that we're willing to take that risk.
I see. So if it was expensive before, the worst case is it'll be as expensive as it was before. Okay. Because there is a certain kind of a Schrodinger's cat there where it's like, okay, we're going to open the box. Are we going to get an allocation? Are we not? Well, we were getting allocations every time before. So
exactly. So if you
it could only be better.
Before, you're no worse off. You might as well. If you weren't, well, now you have to understand how likely is it that you will be successful in getting a pooled array versus one being created for you. And so we're much more hesitant to use it in that latter situation. The typical, there are a variety of cases where this shows up, but one of the most common cases, I mentioned that this relates to span, is ArrayPool goes really nicely hand in hand with stack allocation. So if I had a method, I don't know, compute something, and let's say this is taking in some byte array, and I'm going to do some manipulation to compute some number. Oh, that's funny.
That is interesting. So where is that coming from?
Yeah. So let's say what I needed here was, I don't know, a span char. And I wanted to do something here and use that to return some number at the end. And let's say I needed this span char to be the same length as this incoming array, which is a pretty common situation. Maybe you're going to take in some UTF-8 and you're going to transcode it to UTF-16 to do some analysis on the chars, and then you're going to you no longer need the chars, so you return the array if you rent one. So I could just always say array pool char rent array.length, and then down here array pool char shared return array, and return whatever I wanted to. Temp return, and here I could use it. But we're always going to be hitting the array pool then, and there is some cost to accessing the array pool, right? There's, I don't know, 10 nanoseconds, 20 nanoseconds, depending on situation. So what we often instead try and do is, well, let's have a span char, and ideally, if the length of this array is less than some limit, let's say 256, then I'm going to stack alloc. Got formatted strangely. Then I'm going to stack alloc. Otherwise, I'll rent. But now I have nothing to return. So let me come up here and I'll say array pool array. This will be null. And then here, I'll store that. And down here, I'll say if array pool array is not null, then I want to return my array pool array. So for the super common case where my arrays are short, assuming I expect them to be relatively short, I'm always just stack allocating, and I'm able to. This is basically free. I'll talk about that in a moment, I guess. If not, if I happen to trip over the length, well, then I can pull from the array pool, and then at the end, if I actually pull from the array pool, I need to return the array. And now in here, I can use the span, whether or not it came from the stack or came from the array, and I just operate on that span regardless of where it came from, which again is one of the beauties of span, is it unifies things like stack allocation and arrays. I mentioned that this stack alloc, and again, we're kind of getting off into the weeds, but I mentioned that this is basically free. That's especially true if I were to put this attribute on this method, which requires me to opt into unsafe code. Oops. I don't know why this goes. Yeah. So by default, the core CLR is required to, the runtime is required to zero out the entire stack frame and to zero out all stack allocation. It's just part of the specification. But the larger this is, the more that zeroing costs. So it's actually not free because I'm having to do some number of instructions to zero this space. If I slap this attribute on it, I basically say, you know what? You don't need to zero this. If there was garbage on the stack, the span will contain garbage, and I'm fine with that. And then it's up to me to ensure that I don't do something bad with that garbage, which is why this required me to opt into unsafe in the project, because it is.
And that garbage, it can be garbage, but it could be reused data from previous things, because I bumped into it.
If you were in a web application and you were processing different requests from different plans,
somebody's social security number is just floating around in space.
Accidentally used that and happened to return that garbage. Now we're for
and I want to make sure I clarify. Maybe I wasn't clear. I wasn't understanding. You just picked 256, but like the stack's like what? It's a meg and 32-bit, 4 megs on.
Depends on the operating system. But typically on Windows, you've got about a megabyte. On Linux, the default size is closer to 8 megabytes. On Mac, by default, it's usually smaller. So this would be about 256. So in this case, this would be up to 512 bytes, basically.
Gotcha.
We typically...
Bytes, not K. Bytes.
Bytes, not K.
Nothing. It's nothing.
We're typically comfortable stack allocating up to around 512 bytes, maybe 1,024 bytes. And then after that, we say, don't use stack alloc. And that aligns with other environments and languages best practices as well. Now, if this were a recursive function, that would be a whole different story, because we'd be changing the size of every stack frame to be large. But for a leaf function, we're generally very okay with 128 bytes, 256 bytes, 512 bytes, etc. One other interesting thing, I mentioned that hitting the array pool is, and I realize we're jumping around a lot. As I mentioned to you before we just started, I've been spending all of my free waking hours and more waking hours than I should be having working on writing performance improvements in .NET 9, trying to get that released. And I'm not thinking 100% clearly right now. But I mentioned there's some overhead associated with renting and returning here. We're hitting this shared resource. And then within that shared resource, we're hitting another shared resource. So there could be contention here on this queue. One of the things that the real array pool does is, while this represents the vast majority of arrays that it stores, it does actually have one small but super fast layer in front of that to hopefully sort of take the brunt of the requests. And that is, it's also got a field for a single array of each length, and that is a thread static. So and this is actually like this, whatever number we used. Every thread then ends up being able to store one array of each length. And this kind of thread static is super fast to access. And so what ends up happening is when we go to rent, rather than starting here, there's actually first a check here where it'll say something like, let me pull this out. So this will be index. And then here we'll say, we're going to look up in TLS whether there is an array. What did I do? National over.
It's not null.
Oh, thank you. Then this will say if TLS is not null, it will store the array. Why is it? Oh, I already used that name. Tip. It'll basically pull the array out of that TLS slot, null it out, and return it. And this way we're able to hit that really fast cache before we get to the one that's shared, because no one else can be accessing this at the same time. Only the current thread can be used. So there's no contention on this. And then we go to return. Again, before we do the more complicated thing here, we'll do the same thing with the TLS, and we'll say maybe if TLS is null, then TLS equals array, and we return. So we can, put the thing there. Or maybe we have a policy where we prefer more recently used things. So if it wasn't null, we could then put the current one in there and take the one that was there and push it into the queues or something along those lines. But this takes, for situations where you're just doing a very quick rent something, use it and put it back, maybe at high frequency, this makes a huge difference in the overhead associated with renting and returning with pool.
That point you just brought up something really interesting, that there's the usage model. I've been thinking about memory, because everything's been about memory, and now it's like, well, the usage model. Am I going into my pool, every once in a while for big stuff, or am I in a type loop or a series of type loops in the middle of a recursive function, and I'm going to the thread pool millions of times a second?
Exactly. And oftentimes, if you were actually within your function, you generally wouldn't write a for loop where inside the loop you rented an array, you used it, and you returned it for the same length.
Right.
You just lift it out. But what if you call a function that you don't own that rents from the array and returns it? It's the exact same situation. And that's very common because you call into a core library function. They do that all over the place. So you very frequently do have these in tight loops where in your tight loop, you're calling some framework API that rents an array and returns it. But to your point, there are other common, we have to factor in all these different use cases. Some of them look like that. Some of them look more like you rent an array and you do a whole bunch of asynchronous work using that array, and then you return it. The chances that you're returning it to the same place that you got it, from the same core, from the same thread to the same thread local, relatively small. Like there's a good chance it's going to end up somewhere else. And those patterns have to be taken into account. For example, we could make renting and returning a whole lot faster if I mentioned we had all those kind of individual lists, one per core. We could make them super fast if the thread only ever considered the one list. And if there was something in that list, it used it. And if not, it bailed. What it actually does is it checks that list. And if there's nothing there, then it round robins through the other ones looking for things there. Why? Well, what if you had a producer-consumer pattern where one thread was frequently adding stuff and another one was frequently consuming stuff? They will never find what they need unless you do that round robining, because one of them is going to fill up its list and the other one's always going to be looking at a list that's empty. You really need them to be coordinating. And so different usage patterns breed different implementations and different trade-offs in those implementations. And anytime we try and optimize ArrayPool, what we're really doing is optimizing one use case and pessimizing some other use case, and banking on the fact that the one we're choosing to optimize for, we're making it so much better that it outweighs any negative impact of maybe a small regression in the one that we're pessimizing.
How do you keep yourself from getting any kind of analysis paralysis? Or what is that quote? Don't let the perfect be the enemy of the good.
Yeah. It's hard. One of the things that we try and do is have a stable of performance tests that we consider to be the answer. And if those come up looking good, then even if some other things aren't as good, we err on the side of saying, all right, those performance tests that we have, we've established those as the answer. Now, every once in a while, that doesn't work out. And you say, all right, well, we need to augment that set with other things because we can no longer say that is the one true answer. But in general, if things make those better, in a thoughtful manner, we say, okay. And if things make those worse in a thoughtful manner, we say, this needs some revisiting. The part where you get into a lot of analysis paralysis is when you change your criteria every single time. And then you're having to constantly revisit whether those criteria that you just came up with are appropriate. And you get into lots of discussion and analysis. And then you never make any forward progress. So as long as we sort of have this truth in these perf tests, excuse me, we make sure that the truth is accurate over time, evolving as we need it to be, and we're just constantly evaluating against that truth. We also do find ourselves facing analysis paralysis, and we usually just get a bunch of minds together and say, what do people think? And you don't rely just on yourself, but you get other people to weigh in, often with different backgrounds. There's a really interesting example that literally happened yesterday. Not to do with this stuff, but I think it's a nice example. One of the interesting trade-offs that we frequently make with exposing new functionality on really common types is how does that impact code generation, in particular code size for something like native AOT, where for ahead of time code generation, all of the code needs to be generated ahead of time, including if you're using generics for any possible generic instantiation that the system thinks might be necessary, because every different type you use with one of these generic types has different code backing it. I'm waving my hands a little bit because some code is shared between different things, but you get the idea. So for a type like dictionary, which is used everywhere, if we add a new method to dictionary and the tools are imperfect about trimming that away, both in general and for specific instantiations where that method doesn't end up possibly being used, by adding that method to the super common type, we may have significantly increased code size by adding this method that needs to be stamped for each generic instantiation that's being used in the application. We added a new piece of functionality in .NET 9 that is one of my favorite things in .NET 9, which is it allows you to do lookups on collections like dictionary or hash set with a type other than the one that's the key. So you might have a dictionary from string to whatever, and you could do lookups on the dictionary using a read-only span of char.
Close enough to a string.
Yeah, close enough. And then you rely on the comparer and a special loop interface on comparers in the dictionary to be able to map them together. And this is great because if you have a cache and you're reading bytes off the wire or chars off the wire, you don't have to materialize a string instance to look up to see whether the data that you want to...
Yeah, which is such a common and tedious thing, and it ends up just becoming a piece of administrivia.
Exactly.
That you have to manage.
But this is relevant because we really want to add that to dictionary. But that's functionality being added to dictionary, which is used everywhere. And so and there's a fair amount of code associated with it. So you end up with a copy of that code for every single use of dictionary. If you have dictionary of int and byte and char and string and object, like you have all these different copies of it. And based on that feedback, when we added this functionality earlier in the .NET cycle, we added it as an extension method on dictionary, which has different sort of analysis rules. It doesn't come along for the ride with the whole type. It's only if you actually call that method with a particular set of generic parameters does it actually affect anything. And so we added it as an extension method, which we've used in the past as a viable approach for this kind of thing. The problem is, for this particular case, the usage sticks because you end up with, because of how generic inference works, if I have a dictionary of string to int, when I call that method, I need to specify string and int and read-only span char. I need to specify all of those generic arguments, even though two of them should have been implied by the fact that I was operating on a dictionary string int. So we've had this there for a couple of months, and we've been playing with it and letting it bake, and we got feedback that this usage stinks. And so yesterday, we actually checked in a change based on revisiting the situation, doing more data analysis, conferring with the right minds. And we basically said, actually, we'll be okay if we just make this instance methods instead of extension methods. And so yesterday, we checked in a change that switched them back to that. But it gets back to the point of paralysis, analysis paralysis. We had our source of truth, which was make them extension methods in the situation to avoid that problem. But it ended up being sort of the wrong answer. And so we ended up revisiting it with all the right people and coming to a better conclusion. That was a long-winded answer to your question.
No, but that's the kind of long-winded answers that we love here on Deep.net. Yeah. Well, so we are at an hour and 5 minutes. I think it's probably a good place to call it.
Great.
Fantastic. Man, deep.net into ArrayPool and more. Lots of really cool stuff. Thank you so much, Stephen Toub, for hanging out with us today. And again, what do they say at the end? If someone makes it an hour into this thing, like and subscribe, share with your friends. Please comment in the bottom what you want to see and who you want to see in future episodes. And we appreciate you all for hanging out with us.
Definitely.